Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this is the first of 3 videos on flight controls. This one I'll be covering roll and including speed brakes as well. So the contents of this are ailerons, flight spoilers and speed brakes, ground spoilers, the aileron spoiler mechanics, jams, aileron spoiler interaction, and the Max fly-by-wire spoiler system. As always, please treat your company's training and their manuals as the authoritative source of information. Okay, starting with ailerons. The ailerons are powered by hydraulic system A and or B, and the PCUs are in the wheel well. If both hydraulics fail, manual reversion is available from the control wheels. When the control wheel is centered, the ailerons are actually rigged to droop by 1 degree. Gives a slight lift coefficient there. The range of travel for the ailerons is limited by the PCU stroke, and the ailerons can move a maximum of 20 degrees up to 15 degrees down. On each aileron there are balance tabs, and they move in opposite directions to the ailerons to aerodynamically assist their movement. So you can see in the diagram below we've got the wing, then ailerons hinged on that, and a balance tab hinged there. The balance tab of course works by effectively increasing the camber on the back of the aileron. So you create a low pressure area where the camber is increased. That pulls the aileron down towards it. And of course the opposite's true on the back where the high pressure area forms, which pushes away the aileron. Now in addition to the balance tab, there are internal balance panels and weights. These also assist the movement and harmonise the controls, and they're particularly useful in the event of manual reversion, where the controls would otherwise be quite heavy. So you can see I've got marked on there where the balance weight and the balance panel is on the 737, and the hinge points as well. So air will enter the vent from the high pressure side, which on the way of drawing it with the aileron going down is below, and it will enter the cavity and push the balance panel, which of course is attached to the aileron, causing that to move. On the other side you've got a low pressure area, escape through that vent, create a low pressure area, and that will draw the balance panel up to it. The two actions combined help move the aileron. Okay, on to flight spoilers and speed brakes. So as you can see from the photos, the originals have got 4 flight spoilers and 4 ground spoilers. Classics have got 4 flight and 6 ground. The NGs and the Max both the same with 8 flight and 4 ground spoilers. The spoilers can deploy either asymmetrically to augment the ailerons, or symmetrically when being used as speed brakes, and any combination thereof. Half the flight spoilers are powered by system A and half by system B. So it's inboards and outboards on the classics and the originals. With the NG and the Max, it's every other one. There's no manual reversion facility for flight or ground spoilers. The flight spoilers, when used as speed brakes, rise progressively less from inboard to outboard, and this is to reduce the wing bending moment. The photo I had of this, the one you can see on screen, didn't show it particularly well. At least the contrast wasn't good enough to see it easily between the ends of the spoilers and the wing behind it. So I've just marked in red where the ends of those spoilers are, and you can see that the amount of deflection falls off as you go further outboard. And I say that's to reduce wing bending moment. So, talking of wing bending moment, let's have a look at the load alleviation system. Now, the background to this is that winglets increase the wing loads and the bending moment of wing, and that's due to two reasons. One is their weight, because they weigh, you know, a few hundred kilos each set, but also, of course, they change the lift profile across the wing. Now, 737s built with winglets at production were provisioned for this by being built with a strengthened wing box to counteract this effect. But any 737, either classics or NGs that were retrofitted with winglets, don't have the strengthened wing box of wings with production winglets, and it's just impractical and cost prohibitive to retrofit a strengthened wing box. But of course, winglets are retrofitted, so the load alleviation system came about for that. Now, since the use of speed brakes further increases the wing loads, the combination of using speed brakes and retrofitted winglets on an unstrengthened wing box could cause a structural exceedance if the dynamic loads, and by dynamic loads I mean things like gusts and turbulence or what have you, are encountered when speed brakes are used when manoeuvring, and that's particularly true in roll or side slip and above certain weights and speeds. Now you can see over the image I've got to the right, I've actually listed some of the factors that affect wing loads and bending moment factors. So the first one I've listed there is winglets, as already said, because the weight and the aerodynamic effect, you know, the lift factor they give, so they affect the outboard section of the wingboard of the bending moment. Airspeed, that affects everything fairly uniformly, but obviously that increases with you know, the loads and the bending moments increases with airspeed. The time this is most obvious is if you've ever been a passenger on an aircraft, particularly, you know, one of the wide bodies, you know, 747-400 or A340, and you'll see on the takeoff roll how the winglet, the wing tips lift, and they raise by, I don't know, I mean, I'm no expert on the wide bodies, but it certainly looks to be about 6 or 8 feet. So that there is a vivid demonstration of the effect of airspeed on the bending moment of a wing. Aircraft weight, again, if you know, the more weight, the more lift the wing must generate. And the use of speed brakes, now this affects particularly the mid and the outboard section, but obviously it is putting quite a load on the wing. Then there are the static loads. So these are, well, manoeuvres up to 2.5 G. The aircraft is stressed to withstand. And static loads can be anything from a roll manoeuvre through to just pitching up. So either pitching up, say, a takeoff, or pitching up maybe in a TCAS avoidance manoeuvre or something similar, or just changing flight levels. Then there are the dynamic loads, and these are the ones that are difficult to predict. Now I've mentioned gust and turbulence, but you know, obviously this can take many forms. I mean, it can be anything from mountain waves to passing near a CB. But all of those things, you know, or even clear air turbulence, but all of that, you know, can create dynamic loads. So to reduce the wing loading due to the speed brake, now obviously not because of the other factors, but the one you can control and reduce is loading due to speed brake. So on aircraft with unstrengthened wings, so again, classics or NGs with retrofitted winglets, Boeing have installed a speed brake load alleviation system, and you can identify whether you've got this fitted by simply looking at the placard on the speed brake lever. If you've got a 50% marking, then you are in an aircraft with winglets, and those winglets were retrofit. and the low alleviation system is installed on your aircraft. So this kicks in when you fly above 320 knots and at a certain particular gross weight. Now the actual gross weight depends on which series of 737 you're flying. As an example, for a 737-700 with retrofitted winglets, that trigger weight is 64,860 kilos, which is quite high, but that's the figure. So again, this is only an issue at high weights. At low weights, the loading is less. Now, what will happen is that the speed brake lever will move back to the 50% mark when the last kicks in. When you're over 320 knots and over the trigger weight, you can override it. You can move the speed brake lever back and beyond 50% if you need to, but the control forces will be increased on the speed brake lever. And incidentally, the speed brake lever will remain stationary if moved to up with the load alleviation active. Again, Boeing assumed that if you're overriding it and you've overridden those increased forces, you must have a pretty good reason for doing so. So again, talking of speed restrictions, kind of following on from that, most aircraft have got no restriction on the speed at which speed brakes can be used. I mean, they are actually designed, for the high-speed regime, but they can be used at any speed. But the resultant position of the spoiler panels is a function of airspeed due to blowdown. So at high speeds, the panels will blow down slightly for aerodynamic forces. Now, I say most aircraft have got no restriction, but there were a few aircraft, just a couple of hundred at the beginning of the production run, for which Boeing issued FCOM Bulletin 19 for the NGs, called Elevator Tab Operation Limits, and this basically prohibited the use of speed brake above 310 knots due to vibrations being caused on the elevator tabs. Now, a service bulletin was issued which gave a fix for this, and modified aircraft should have had that restriction lifted. Well, modified aircraft will have had that restriction lifted. This was issued back in 1999, and there shouldn't be any unmodified aircraft still in service out there. But you never know. There could be some. If there are, you will know it because this bulletin will be still current in your FCOMs. Okay, well, by way of proof for you, I guess that that speed brakes can be used at any speed, and in fact beyond VMO or MMO. I want to show you a video clip which was taken by an FO of mine during an air test, which demonstrates the use of speed brakes at high speeds and shows their effects. Okay, so let me talk you through this. This is a high-speed handling check on an air test. So I'm going to gently accelerate the aircraft up to 360 knots in a gentle dive, just being very light on the controls. First thing we're looking for is the VMO overspeed clock, at what speed that comes on. So that was about 348 knots on the FO side. We record that. So continue the acceleration just gently up to 360 knots. And at that point, I just do gentle handling check, just fingertips on the control, just to make sure that it's all handling normally and feels right. Now I'm going to take my hands off the controls, covering them, apply the speed brake, so there's no roll there, and the vibration isn't undue. Okay, on to ground spoilers now. So a word about the logic, because it's been different on every generation of 737, or just slightly different, but let's say enough to confuse. So on landing, assuming you've armed the speed brakes, flight spoilers will deploy when the thrust levers are at idle and any two wheels have spun up to at least 60 knots. Now, the first difference as caveats for that is that on the NGs, the rad alt must be below 10 feet, and on the Max it must be below 6 feet. Incidentally, the difference between those two is because the Max stands taller with the undercarriage, but obviously the rad alts are still in the same location. So basically, 6-foot rad alt on a Max is pretty much the same as 10-foot rad alt on an NG. Anyway, I digress. Now, the ground spoilers will deploy when the right main landing gear strut compresses, except on the Max, which requires compression of both main landing gear struts. Now, additionally, if you haven't armed them for landing, if you've forgotten or whatever, the speed brakes will deploy when reverse thrust is selected on the NG and the Max, not on the originals or the classics. After an RTO or landing, if either thrust lever is advanced, the speed brake lever automatically moves to the down detent and all the panels retract. That is the one rule which is absolutely universal across all 4 generations of 737. But I say all the rest have got slight differences. A little bit confusing, but the basics are that when you touch down, when you get pressure on the struts, the ground spoilers will deploy for the right strut. The flight spoilers will deploy at wheel spin up, and the ground spoilers will deploy at right main landing gear strut. Okay, on to the SFPs, the short field performance aircraft. Now, on the SFPs, the flight and ground spoilers move more on the ground than non-SFP aircraft, and this is to improve stopping distance. It's just form drag. That's all this is. Now the non-SFPs, which is in the upper picture, you can see that the outboard flight spoilers move to a maximum of 33, and the inboards move to a maximum of 38 degrees. The SFPs, they move much further. They move to 56 and 65 respectively, although interestingly they actually return back to their normal position once you've decelerated through 60 knots. I guess they thought it was no longer necessary because obviously form drag is insignificant below 60 knots. But there are the differences anyway. Obviously the ground spoilers, as you're probably aware, certainly the outboard ground spoiler does deploy more to 60 degrees. Alright, the aileron spoiler mechanics, let's have a look at that. And really the roll system is quite good in this respect because you can see most of this in action in the wheel well. But before we get there, let's just have a look in the flight deck and discuss exactly what happens, because I think in the FCOM is slightly misleading in this respect. The FCOM implies that the captain's control wheel drives the ailerons and the FO's control wheel drives the spoilers. Now, that isn't quite the case. I mean, it can be under certain circumstances, but in normal operation, the captain's control wheel operates the ailerons, which in turn operate the spoilers. And the mechanics of that happens in the wheel well, and I will come on to explain and demonstrate that to you later on. Now, the FO's control wheel is connected to the captain's control wheel, as we know. You move one, the other one moves, and that happens through the aileron transfer mechanism. Now, in normal operation, the aileron transfer mechanism, which is a unit located under the base of the FO's control column, this transmits the movement of the control wheels to each other by cables and a torsion spring. So this allows either pilot to operate both the ailerons and the spoilers through the captain's cables. However, there's a loss motion device built into this aileron transfer mechanism, and that means that the the FO's control cables effectively float. They're driven by, well, they're back driven by the powered aileron system through the aileron spring cartridge. Again, this is in normal operation. Now, in non-normal situations, then it goes back to the captain's control wheel drives the ailerons, and the FOs can drive the spoilers. So if the captain's control wheel or the aileron system jams, roll control is available through the FO's wheel to move the spoilers by overriding the force of that torsion spring that I've mentioned, which is in the aileron transfer mechanism under the FO's control column. And that requires a wheel load of anywhere between 80 to 120 pounds. There is also a force to be overridden in the aileron spring cartridge. That's about, well, it's actually painted on, stenciled on in big letters. You can see it for yourself in the wheel well. It says on 92 pounds. But obviously you're already giving that by overriding torsion springs. So the two don't add together. One input of 100 and odd pounds will override the two. So don't worry that this is going to be unmanageable. It isn't. The thing to bear in mind is, if you find yourself in this situation, and let's hope it's only in the simulator, is that the lost motion device, there's a lag in that, and that engages at 12 degrees of control wheel movement, and that gives a delay to the input. So this is only when we're talking about a jam in the captain's side or the aileron side. So if you're using the breakout mechanism and you're turning with the FO's control wheel, you will have that delay to input. Now, if it's the other way around and the FO's control wheel or anything in the spoiler system jams, then roll control is available through the captain's wheel to move the ailerons by overriding this 80 to 120 pounds of force in the torsion spring in the aileron transfer mechanism and the aileron spring cartridge. But there is no lost motion device under the captain's control wheel, so you don't get that delay to input. The input's clean on the captain's side. Alright, this is not a photo that you will see every day. It took me a while to get this one. This is looking into the forward equipment hatch, and we're looking up and aft under the control columns. So this hatch, it's the small one ahead of the E&E bay. So further forward than that, you open the hatch, you can see the hatch door at the bottom, and we're looking up to the floor of the flight deck. Now you can see I've labelled on the left and right side two sort of cylinders. These are the bottom of the control columns. So the control columns extend up from those 2 points there. They're your control columns. Now on the left hand side, because don't forget we're looking aft, so that's the FO's side. You can see I've marked on part of the cylinder. You can see that part of a drum, that's a bus drum, and there's another one on the captain's side, and they are connected with the two cables I've marked there, which are sheathed in plastic to avoid any binding on them. So there's a cable that makes a circuit around those two bus drums to connect them. So if the FO moves his control wheel, the captain's control wheel moves, and vice versa. That's how that mechanism works. Now on the captain's side, there's another drum below it, just a few inches below it. It's difficult to say. I haven't marked on the second drum because it was getting a bit confusing with a bit busy on the graphic. But what you can see are two cables coming up from that shaft. They are your aileron input cables, so they run from the captain's control column down under the floor of the cabin and pop out in the actually just above the wheel well, and I will show you that in the next graphic. On the FO side, you've got these are actually labelled as auxiliary spoiler input cables. So these are only used when there's a jam in the captain side or the aileron side. So in ops normal, these are just floating in effect. But if you need to break out and use them, they are the direct connection to the spoiler system from the FO's control wheel. At the base of the control wheel, you can see it looks a little bit different to the captain side, and that's because you've got the aileron transfer mechanism there and the lost motion device. That's what the extra mechanics is there. So, coming back to the wheel well, and this photo is the wheel well of the NG. It's very similar to the classics. What I've labelled there is the input shaft. Now, above that input shaft, just above the ceiling of the wheel well, there is a drum which has those two cables that we saw coming back from the base of the captain's control wheel. Those cables rotate that input shaft. Now, the other input that's available to the ailerons is from the autopilots, and to the left, as you're looking forward in the wheel well, you can see two large actuators there, and they are the aileron autopilot actuators. You can see just below them there's a green control rod and a white control rod to its right, and the white control rod there attaches to the input shaft. It's on a crank from the input shaft. So the either aileron autopilot actuator, if it moves, be it A or B, or indeed both on autoland, will move the aileron input shaft. Now, at the bottom of the shaft, we've got the aileron feel and centering unit, which you'll have read about in the FCOMs. Well, that's it. That's what it looks like, and the aileron trim actuator. And they can both rotate the input shaft as well. And you know this because when you move the aileron trim, you see the control column turn. So that's your input there. So there are those three inputs to the aileron system. Where do the inputs go? They travel along these. They're called pogo inputs, which I can only imagine because the aileron input shaft looks like a pogo stick. But anyway, that's their official name, pogo inputs. This isn't just something I've made up. You will see that there are horizontally there four control rods that come from the input shaft. They're attached. It's actually behind as we look, so it's a little difficult to tell, but take my word for it. Each one of those is on a crank from that input shaft. This, by the way, is the only difference from the NGs to the classics. The NG has got four of these. The classics only have two, one per aileron PCU. So, what do? They transmit the input from the input shaft to the aileron PCUs, and you can see we've got two. We've got the B system PCU on the top and the A system PCU on the bottom. So they give an input to the aileron PCU. The aileron PCU uses the hydraulics to magnify that input and use the force of the hydraulics to move by those two large white kind of crescent-shaped bars that go across to the aileron body quadrant over there on the right. Now you can see on that aileron body quadrant, which I say is turned by power from the Aileron PCUs, there are two cable runs on that quadrant. The bottom cable run, you can see, actually comes across the photo, goes behind the pulley just to the left of centre of the photo, then across to the next pulley there, and goes out to the left aileron. The top one of the two does the same, but off to the right aileron. So they're your components. That's how it works. That's how the movement from the control wheel is translated into movement at the ailerons.
Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech site. And today I'm coming to you from Cranfield University and their Boeing 737-400 to have a look at the Aileron spoiler system on the aircraft. Now, although we're in a classic, the system is virtually identical to that on the NG. There's one minor difference which I'll point out as we go around. Okay, so if you remember, the main input into the Aileron spoiler system is from the captain's control column. The captain's control column is also interconnected with the FO's control column, but all the main inputs coming through the captain's side. So what we're looking at here is the aileron input shaft, and this rotates, and on top of it there's a quadrant and a pair of cables which run up to the flight deck and come down from the captain's control wheel. So this is a direct cable linkage from the captain's control wheel. As the captain's control wheel is rotated, so this aileron input shaft rotates. As it rotates, you can see it's connected to these two pogo inputs, as they're called, and this is the one difference from the classics than the NG. The NG has got 4 of these, so it's got another pair up here, but on the classics we've just got the one pair. And these connect to the Aileron PCUs. So you've got the B system PCU here and the A system PCU down there. They give the input to the PCU. The PCU then uses its hydraulic power to throw the crank and move this shaft here. And this is the aileron control column. And on it we've got these two quadrants. And these quadrants actually hold the cables that go out to the ailerons. So you can see there's a terminator there for this cable, and the cable comes along, goes out around the pulley and off up to the left hand wing. So that's your left aileron linkage there, and the right aileron is the same above it. You've got a terminator on the cable. Cable comes around the quadrant. This then goes across, round the pulley and up the wing to the right hand aileron. So that's the basic control wheel input to the aileron. Now, in addition to that, you know that the ailerons can be controlled from the autopilot, and the autopilot actuators are located here. So you've got autopilot A, autopilot B, again a couple of actuators, and they move these linkages, these two linkages here, and they're interconnected. So if just the A moves this linkage, if the B moves, it moves this linkage. Both linkages run through to the aileron input shaft. So again, they will rotate the shaft, causing motion in the PCUs, causing the aileron control quadrant to move, causing movement of the ailerons. The final thing to mention on the aileron system is down here, and this is the aileron feel and centering unit. Now, you know in the flight deck when you turn the control column with hydraulics off, so say on the turnaround, if you were to just move the control column and release it, it would move back to the center position, as it would in flight with the hydraulics on. That center position and that feel comes about from these springs here. You see there are two fairly heavy springs. That's your feel. There and there. That's what gives you the sense of resistance when you're moving the control wheel. They also are spring loaded back to the neutral position, and that's done by a cam which is attached to this aileron input shaft. The cams are kind of a sort of a curvy triangle shape, a concave triangle. So there's a dip in it where the roller will naturally want to sit. That's your central position. Now we can adjust that central position with aileron trim. So if aileron trim is moved in the flight deck, it actuates this little motor here. Behind the motor there's a little push rod, and that moves, that physically rotates that cam and this whole aileron feeling and centering unit round so that it adjusts the neutral position for the ailerons. Okay, well let's see that in action, shall we? And I'll get my colleague to switch on the hydraulics and move the ailerons. Hydraulics and ailerons, please. Hydraulics and ailerons. It will be loud with the hydraulics on, so I may not be able to speak over it once the hydraulics are on. If you can hear me, you can hear that the hydraulics are on. We've got the inputs from the control wheel here. Moving the pogo inputs. These are the Aileron PCUs. Moving the quadrant, and the quadrant is moving left and right. The cables are moving. Okay, so the hydraulics are now off, and I've asked my colleague to again exercise the control wheel. So what we're looking at here is the manual reversion case. So you can see that the control inputs are still coming in. So my colleague's moving the control wheel left and right, but we've no hydraulics on now. So this is your manual reversion case. Again, the power inputs are going across to the PCUs, the Aileron PCUs. But notice that what's happening is the whole PCUs are being moved. This is part of the reason why it's so heavy work on manual reversion. But they're moving, there's no actual in and output from those, but they are being moved to physically turn the aileron control shaft, which again, as you can see, is moving the ailerons. Okay, thank you for the ailerons. Alright, what I'll do now, I'll just switch positions into the other wheel well, and I'll show you the spoiler system.
Okay, let's just have another word about aileron trim. As I explained earlier, it moves the neutral position by rotating the feel and centering mechanism, which you can see there. Now, you may have wondered, or may not, but either way, I'll tell you why there are two switches in the flight deck, and this is simply to prevent spurious electrical signals from applying trim when you don't want it. So the forward one is actually the directional control one, but it won't do anything unless you move the aft one at the same time. The aft one's simply an earth return. It's like it's a bit like saying, you know, are you sure you want to move either, you know, left aileron trim or right aileron trim? So the two must be used together to cause the aileron trim to move, which of course we know and we do instinctively, but I just thought you might like to know. But try it next time you're in the flight deck, on the ground, pop the hydraulics on and just try turning them. You can move these in different directions, so you can move the top one left and the bottom one right. The aileron trim will move left, because it doesn't matter which way you move the bottom one as long as you move it to give that earth return, and the same if you try to the right as well. Just a reminder that use of aileron trim with autopilot engaged is prohibited because there's potential for excessive roll when the autopilot is disconnected. So there we go. Right, I'll show you a little video now of a close-up of that the aileron trim actuator in action. But before I do, this is the camera angle that I took the video from. I just want to draw your attention to these components so that you can see what's happening. So the aileron field and centering unit is the upper of the two units. The trim actuator is the sort of rectangular box, the lower rectangular box, and you can see the electrical connection going in. There's a little electric motor which powers this, and you'll hear it in the video. The thing to look out for is the aileron trim actuator piston. So you can just see it in this shot, but it's not always visible because of the angle I was holding the camera at. That piston there is what is physically pushing and rotating the aileron input shaft around, causing aileron input. Now, if you want to actually see the output, the kind of proof that this is having an effect, then keep your eye on the cable at the top of the picture, just running slightly diagonally across from the quadrant. You will see that move as the aileron trim actuator moves. Okay, let's see the video. Okay, so first of all, my colleague's operating the aileron trim, but he's operating it without the hydraulics on. So you can see that although the field and centering unit is turning, the aileron input shaft isn't. And you can see that by the ribs. Now the hydraulics has gone on, and did you notice that the shaft actually turned a little to take up the slack and move? Now he's using the aileron trim again, and if you look below the obvious thing that's turning, you can see the piston extending. There we go, and that's turning that aileron input shaft around. Now he's coming back the other way. Now what I want you to do is just look up at the top of the picture, and you'll see a control cable just moving diagonally across. That's the aileron. That's the actual cable that goes to the aileron, and you can see it's moving. So that tells you that the ailerons are moving while this trim is being applied, which is of course what you see, out of the flight deck window if you look, or certainly you see it on the control wheel. So that's around about full extent there. There's no more movement. Now he's coming the other way. Again, you can see the whole aileron input shaft turning. If you look at any of the rivets on it, you'll see that they are rotating with the shaft. And again, you can look up at the aileron control cable up there and see that that's moving as well. Okay, onto the spoiler components now. Again, this photo I took is on the NG, but the video I've been shooting is on the Classics. It's absolutely identical, except obviously in this photo the wheel wel's a hell of a lot cleaner. Interesting, none of these components are present on the Max. The Max has got a fly-by-wire spoiler system, and all of this is gone. But let me take you through the components that are there on every other generation of 737. So at the bottom you've got the aileron spring cartridge. That's the bit that connects the aileron system to the spoiler system. it's I say it's a spring cartridge. So at the left of the picture where it's green, that's the inner piston. Where it's white, that's the kind of outer cylinder. And there's a spring inside, which, as written on the decal there, 92 pounds override, which is used to disconnect the two systems. But in normal operation, that as you can see, it attaches to a crank on the spoiler control quadrant shaft. That shaft, by the way, is the one which turns with inputs from the FO's control column in the event of a jam. Now, that thicker green bar at the back of the picture there, that is the input to the large white unit on the left from the spoiler control quadrant shaft. So that is the input. So the spoiler mixture and ratio changer, a huge mechanical unit, and I've only seen the inside of this once, and it looked like a grandfather clock. There were so many cogs and pulleys and cables in there. It was actually a mechanical work of art. But mechanical is definitely the operative word, and it's all gone on the max. But what this does is it changes the it puts in the right amount of spoiler for whatever aileron you're using. That's essentially what it does. Now the output from that is there, and that goes across to the ground spoiler control valve. And if the aircraft senses it's on the ground, then obviously you will need more spoilers going up to full ground position, and the ground spoilers as well. So that's where the input from that comes. The output from that spoiler mixer ratio changer is the cables to the individual spoilers, and I've not marked them on this graphic. They're difficult to see, but you can just see one diagonal cable just slightly below that below that last rod I've indicated there.
Okay, so now we're going to look at the other half of the system, which is the spoiler system, which is interrelated to the ailerons, because obviously, as you know, when we move ailerons, the aircraft also just deploys differential spoilers to assist with the roll control. So you recall that over on the left hand side of the wheel well we had the aileron movements there. Now there's an interconnection between the ailerons and the spoiler system, which is over here, which is here with the aileron spring cartridge. I'll show you this moving in a moment, but suffice it to say, as the aileron control shaft rotates, moving the ailerons are on these cables, so this aileron spring cartridge moves as well. That, as you can see, is connected to this, and this is the spoiler control shaft. This controls the spoilers. Now, out of interest, this is also connected back up to the first officer's control wheel. So if there's a jam in the captain's control wheel, or any of the cables coming back, or indeed any of the aileron system, then the first officer can turn his control wheel independently, because there are torsion springs underneath which will release the interconnection between the two control wheels, and the inputs from the first officer's control wheel will come down and will move the spoiler system to give the aircraft some amount of roll control if the ailerons are disabled or jammed in any way. Okay, so back to the normal system. So the normal way that the ailerons, the spoilers, sorry, are moved is as a result of movement in the aileron system. So the aileron movement does its thing here. It's transmitted across on this aileron spring cartridge, and that causes movement, rotational movement, of the spoiler input shaft here. Now, at the top of this, almost at the top, just an inch or two below the ceiling, there's a green bar going across. Do you see that? That gives the input into this, the spoiler mixer and ratio changer. So, the spoiler mixer and ratio changer is actually 2 units. This is the spoiler mixture where the engineers rig the aircraft so it has the right amount of spoiler deflection for aileron deflection. But behind that, you can just see the edges. There are a lot of quadrants. There are actually, I think from memory, at least 4. Might be difficult to see them, but see a couple of quadrants there. Great. Each one of those quadrants has got a cable coming off it. You can see the cables here. Those cables run out up the wings to the spoilers. Now, one of the differences between the spoiler system and the aileron system is that the spoiler system has got the actuators actually out there at the surfaces. So the hydraulic actuators are out on the wings, whereas here we know that the hydraulic actuators, the PCUs for the ailerons, are there in the wheel well. These 2 units here. But anyway, we've got, as I say, 4 or 6 lots of cables coming out for flight spoilers and ground spoilers there. So that's how they're moved. Now, there's one other piece of the jigsaw, which is this bar here. This green bar coming out of the aileron spoiler mixer unit connects here to this. And this is the ground spoiler control valve. So, obviously under certain situations, certain conditions, we'll need to operate the ground spoilers. That's when the aircraft knows that it's on the ground. So there's a weight on wheel switch, comes from the right landing gear, comes across, and that talks to the spoilers, and that will give you ground spoilers as well. Let's see if we can see this in action with flight deck inputs. Can we have ailerons, please, again? So again, what we've got here is we've got movement of the ailerons. We've done this on the manual version, so it's quieter. You can see the motion coming across with the spring end on the spring cartridge. It's moving the spoiler control shaft. Let me get a little bit more of that.
Alright, the last piece of the jigsaw really is the actuators, which obviously I couldn't show you from the wheel well. And they are located on the wing under each spoiler panel, and you can see them marked there. The ailerons, though, they don't have actuators per se. They've got PCUs, and they are in the wheel well, as we saw earlier. So the ailerons, the motion for that is transmitted to the surfaces by cables to a quadrant in the wing that operates a rod attached to the aileron, and you can actually see the aileron pulleys and cable run going out. All right, so let's try and rationalise everything we've covered, because there was quite a lot in that, and let's have a schematic. What I'm going to do, I'm going to build this up in 2 sides. We're going to consider the aileron system on one side and the spoiler system on the other side. And down in the bottom right there, you can see I'm going to be using blue to show a cable or a mechanical connection. Green for hydraulics, and any electrics are shown by a little black line. So let's go through this. Okay, it all starts at the captain's control wheel. Mechanical connection down to the aileron input shaft. This, you've seen, runs all the way along the underfloor of the cabin, comes out at the wheel well, and rotates that aileron input shaft. The FO's control wheel is interconnected to the captain's, unless there's a jam, and it's interconnected by the aileron transfer mechanism. The other input to the aileron input shaft is from the autopilot, and we saw those autopilot actuators on the left of the photo. The 2 actuators for that, A and B, and the last input possible is from the aileron trim switches. They feed electrically down to the aileron trim actuator and across to the aileron feeler and centering unit. From there, the input goes to the aileron PCUs. They can be operated either by hydraulic system A or B, or by manual reversion, by physically moving the PCUs themselves. That puts an input into the aileron body quadrant, which sends the cable movement out to the wings where the ailerons are moved. Now, the aileron body quadrant also has an output to the aileron spring cartridge, unless there's a jam, and that has an input across to the spoiler control quadrant. And in this way, the spoiler system is connected to the aileron system in normal operation. In non-normal operation, there's a connection down from the first officer's control wheel. If there's a jam in the captain's either control wheel or anywhere on the aileron system. The speed brake lever and the spoiler control quadrant both input into the spoiler mixer and ratio changer, which talk to each other, sort out all the mechanics of exactly how much spoilers and on which side it's going to need. The output from that goes down to the spoiler actuators, and through hydraulic system A and B, the flight spoilers. The spoilers, if required, you can shut off from the flight deck on the flight controls panel with the spoiler shut-off switches. When you do, you'll see the low pressure lights illuminate. The last thing from the spoiler mixer and the spoiler actuators is the inputs from the ground spoiler control valve. So if it senses we're on the ground spoiler actuators will operate from hydraulic system A, and the ground spoilers will deploy. There you go. That's the full schematic. Alright, let's talk a little bit more about jams and the various safeguards we've got. We've already mentioned many times the Aileron spring cartridge. This is the big one. I say its normal function is to transfer movement of the aileron system across to the spoiler system. However, if there's a jam in either system, this spring cartridge will compress or extend as the working system operates to isolate those two systems. That's what that does. Now, other ones that are present, and there are many of these, and I'm only mentioning these just to kind of give you guys confidence that there are many fail-safes in the mechanism. But if by any chance the aileron spring cartridge jammed, or it didn't function properly, or the spring had seized, or whatever it might be, the FO can still override that spring cartridge by breaking the shear rivets at the bottom. There are 4 of those. I don't recall how many pounds of force is required, but obviously it'll be more than the 92 of the spring cartridge. And with that, the FO can move the spoiler control quadrant shaft. Another mechanism is what's known as the breakout mechanism on the spoiler control quadrant shaft, and that's just there in case there's a jam in the spoiler mixer and ratio changer. I say a lot of heavy mechanics in there. If that were to jam, then this would isolate that and limit the force that goes into that changer to prevent any damage to those components. Alright, that's enough of jams and things. Let's look a little bit more at the aileron spoiler interaction. Again, I've talked a lot about this, so let me just summarize it by saying that this unit, this is where the spoilers augment the roll control, even when simultaneously being used as speed brakes. It's a very clever piece of mechanical kit. So what does it look like from outside? So many years ago now, before testing a 737 Classic, I I mean, this was one of the checks I did. I actually went outside, as part of the pre-flight checks, and got the flight controls to be moved so that I could satisfy myself that they were, it was all wired up correctly. And one day I decided to take photos of it. So here are those photos, and what I'm showing is how the spoilers move with various combinations of aileron and speed brake. So these first two photos are taken with the speed brake lever down. The top one is with the control wheel neutral. So speed brake lever down, control wheel neutral, nothing's deflected, as you would expect. The bottom photo shows, again, the speed brake lever down, but with the control wheel full right. So you can see with control wheel full right, we got the aileron coming up on the right wing, going down on the left wing. But in addition to that, you notice that we've got some flight spoilers deflected. This is what you'd expect because they are augmenting the ailerons and giving extra roll control. And in doing so, they're doing that at a more inboard section of the wing so that there is less wing bending moments occurring. Or what wing bending moments is occurring is happening in a more strengthened part of the wing. Okay, on to the next one. This photograph is the same as the other one, but with about half speed brake. Now what you can see on this is when when my colleague applied the control wheel full right, not only did the spoilers on the downgoing wing rise, but also the spoilers on the upgoing wing fell. So one lot went up and the other lot went down. Much like the ailerons. Now that property of the spoilers on both wings to respond to roll inputs, that's known as differential spoilers, and it only occurs when the speed brake is in use. And this is why the roll rate increases with speed brake extended. Because you can see, if you just for a moment think of those speed brake panel or those flight spoiler panels as extra ailerons, you can see in the bottom photograph one's gone up and the other's gone down. So you can see in the photograph you're almost doubling your aileron area. So you're increasing the effectiveness, which will increase your roll rate, which we know it does. All right, so here's the last photograph, and this is with the speed brake lever at full flight detent. And you can see that the spoilers rise further on the downgoing wing. So even a full flight detent, you still get more of this differential spoiler effect. The thing that I guess not to be distracted on with this photograph is the ground spoiler deployment, because the aircraft's on the ground. So yeah, now I'll come on to this. The speed brake lever, when the speed brake lever reaches, well, it's actually a few degrees before the flight detent position, the ground spoilers deploy because the aircraft's on the ground. Now, what I want to draw your attention to with this, this is a real warning to you. What you don't want is to see those sort of images when you're in flight. And it could happen. If you've got any sort of technical problem which could be due to a faulty air ground sensor, and the obvious one is landing gear will not move up after takeoff, the QRH procedure, it says caution, do not use the speed brakes in flight. Well, these photographs are showing you exactly why you don't want to apply speed brake in flight, because if you do and the aircraft thinks it's on the ground, you'll get the ground spoilers as well. Okay, nothing much to say about this slide other than I've just pieced all 6 photos together for you, just so you can see it for your comparison. If you want to look at that at your leisure, by all means do so. Just pause the video and take it in. Okay, for those of you flying NGs with the optional control surface position indicator, display, then you can see this effect from the flight deck. Let's have a look at that. So this is the control surface position indicator. I'm going to start by moving the ailerons to the left. And you see that that brings the flight spoilers up on the left, as you'd expect, and to the right it brings the flight spoilers up to the right. That's normal operation. Okay, now this time I'm just going to use part speed brake. So you see the flight spoilers have deflected there, and this time as we turn left, the left spoiler goes up and the right spoiler goes down. As we apply right aileron, right spoiler goes up a bit more, left spoiler goes down a bit. Now we're going to take full flight spoiler with left aileron. What happens is the right flight spoiler goes down. With right aileron, the left flight spoiler goes down. There we go. Alright, on to captions now. So the ones we've got, well there are three in all, but let's have a look at these two first. So there's the amber speed brake do not arm light and a green speed brake armed light. And these are both controlled by the auto speed brake module. There you go. You didn't think I could get through one of these presentations without showing you something from the E&E bay. Well, here it is. This is the auto speed brake module. And this too, I think I'm probably right in saying has been in, well, certainly in the originals, the classics and the NGs. I'm not sure if it's there in the Max. I don't think it is. Now this unit will sense a main wheel spin up of greater than 60 knots, and it then uses that information to control the automatic operation of the speed brakes. And you can see the wheel spin up light up there at the top left of the unit. One thing to mention is that the speed brake do not arm light actually doesn't preclude its use in flight, and the QRH will confirm this. But you will need to manually deploy the speed brakes on landing. So as I say, don't confuse this with an air-ground issue, where you should absolutely not use speed brakes in flight. This is just an arming function. Alright, the other caption is the amber speed brakes extended light, and this is controlled from the PSEU, which is in the Ford electronics bay. And this light will come on if the speed brake levers is beyond the armed position below 800 radio with flaps greater than 10. Now, hopefully the only time you'll see this is if you've been using speed brake on the approach and put it, or thought you put it back to the arm position, but haven't quite just moved it far enough there. So normally just a very tiny movement of the speed brake lever will extinguish this light. Obviously what it's there for is to warn you that you should not be using, any speed brake. I was going to say a significant amount, but any speed, you should not be using any speed brake at all below 800 radio because of the high rate of descent. I mean, you're clearly going to be in an unstable approach, and that's what it's warning you about. All right, speed brake test. Now these lights, I would imagine not many of you have seen these unless you've been flying 737s for as long as I have. They were only there on the originals and on the early non-EIS classics, which were just 2 or 3 years worth of 300s. Now what they do is they check the speed brake indicating circuits for continuity by simulating failures that the speed brake indicating system should enunciate. So to perform the tests, you put the speed brake lever in the arm position. Obviously this is done on the ground, I hasten to add. So you arm the speed brake and you press these buttons one at a time. Each button performs a different circuit test. So, and I cannot for the life of me remember what each one is. And to be honest, nor do we need to know. All you need to know as a pilot is, you know, if you're in one of these aircraft and you want to do this check, put the speed brake to arm, press button 1, and what you should see is that the armed light goes out and the do not arm light comes on. If that happens, the test is passed. Take your finger off the button, press button 2, and again the same thing will happen. Finger off the button, press button 3, and again the same thing will happen. Now, perhaps surprisingly for such a comprehensive test, all this proves is that the indicating system is operative. It actually doesn't verify if the speed brake system is operative, but you know, it's better than nothing. But for whatever reason, Boeing decided it was a bit too elaborate, and it got removed with the EIS. All right, to finish off, let's go forward about, I don't know, 3 or 4 decades, and have a look at the MAX fly-by-wire spoiler system. This was installed on the MAX to improve production flow, in other words, make it easier to build, reduce weight, because you've seen what that spoiler mixer and ratio changer unit looks like, and those heavy-duty solid bars in the wheel well. All of that is weight. All of that is gone. And improve stopping distances. Great. Well, this is something that we can all relate to. So let's have a look at the fly-by-wire spoilers. This is the schematic that I went through earlier, and this shows the roll control on the NGs. Now, I draw your attention to the 2 areas that I've highlighted in red. So they're the aileron spring cartridge, the spoiler control quadrant, ratio changer, and spoiler mixer. And let me just show you the difference on the MAX now. There. All of those units are gone, replaced with a spoiler control electronics unit, and from the speed brake you've now got a position transducer. There's actually also a position transducer on the FO's control wheel as well, which is why it's now a black electric line rather than mechanical line. So I'll just show you that difference again. So going back to the NG, it looks like that, and on the MAX it looks like that. So a whole lot simpler, lighter, I'm told more reliable, and you know, generally a great step forward. Okay, so in addition to the things like weight and complexity and stopping distance, the fly-by-wire spoiler system has got a number of other functions. So let's take a look at those. Just going back to this, sorry, the wheel well differences, as I've said, that's a photo of the wheel well of the MAX. All those mechanical ones have gone. So on to the other differences, functional differences for us as flight crew. First one is spoiler light. That's down there on the flight controls panel, the new 5th light at the bottom of the stack there. And that indicates a spoiler fault as sensed by the spoiler control electronics unit, which means that 1 or more spoiler pairs are in op. Again, QRH procedure for that. The second feature is maneuver load alleviation, and this replaces the speed brake load alleviation system, which was there, if you recall, on classics and NGs that had been retrofitted with winglets. Now, even though this MLA is there on non-retrofit, because of course all Macs have got winglets, it's there to effectively do the same function. So it'll retract the speed brakes during maneuvers that result in high load factors to reduce the bending moment. But in doing so, in doing that in an active way, not for any particular hard speed, so not for 320 knots and 64 845 kilos or whatever it was. It actually looks at a function of the two. It's much more clever than the old system, and it will use the combinations of those together. I understand with a G input as well. To sort out exactly how much speed brake it will allow you to have, and in doing so, it can ensure that the wing bending moment is reduced, and that allows for a lighter wing box, which allows for a lighter weight aircraft with all the associated fuel burn and performance improvements that gives. So that's the reason behind this. The landing attitude modifier is another one, and this does two things. So flaps 15 to 30, if the thrust is near idle, it's going to slightly raise the flight spoilers to increase drag for a better glide slope capability. This and now we've all flown into places where this is common. I mean, certainly on my neck of the woods around Europe, places like Malaga runway 3.2 degree glide slope, and they're usually on that runway because of the sea breeze. But as you start the approach, the sea breeze isn't there, so you're actually making the approach in a tailwind a lot of the time, even though you'd be landing in a headwind. And how do we sort that out? Well, we either use speed brake or we configure early. Well, this will help us in that situation. If you've done your configuration, you've already got to flap 15 and you still need to do something more, then this will help you out. If it detects that the thrust near idle, it'll give you a bit of flight spoilers for drag. Now, at flaps 30 or 40, and if you get below VREF plus 10, the spoilers will raise slightly to reduce the lift, necessitating a higher angle of attack and a higher nose attitude. And this is to give an acceptable nose gear contact margin. So what it's doing is the nose gear contact is what this is talking about. Now, what this does to your tail contact, well, obviously it'll reduce it, but it's trying to reduce that nose gear contact margin for you, so you don't do a 3-point landing in effect. And then the final function there is the emergency descent speed brakes, and this gives an increased flight spoiler deflection when the speed brakes are used above flight level 300 and the cabin altitude warning is active. In other words, it knows that you're doing an emergency descent, and it will give you more than the normal amount of flight spoiler deflection to help you get down quicker. That's it. That's the Aileron, the spoiler system. As always, if you've enjoyed the video, if you've found it useful, please give it a like, subscribe to my channel if you haven't done so already, and share it. Tell your colleagues about these videos, and hopefully it can help them as much as it's helped you. Thanks for your attention.